In this video, let's do a couple more adding problems and then we will get into some subtraction. But in the previous examples, we talked about, let's say we were adding one negative to a positive and so on. But, let's say we had both negatives and we were trying to use the chip model to do these instead. And of course, you can figure these out on your own. But let's say I was to add a -4 plus a -3. This is a distinctly different case than these cases over here, because here we were adding a positive to a negative. But if we're adding two negatives together, we have a different sort of effect, because say I start with the first number, well, that's a -4. That's like I am in debt by 4. And I add another debt of -3 to that. It's kind of like going on the saying that 2 wrongs don't make a right. 2 wrongs actually make a larger wrong in this case, where, if we have -4 plus -3, we actually end up with -7. And another rule that, you may have heard is if you're adding negatives, you just add up the absolute values of the results, and what you end up getting is a larger negative. It works exactly the same as addition of positives. And we could equate the situation to 4 plus 3, where it's an equivalent situation, right? Because 4 plus 3 is 7. -4 plus -3 is -7. The only difference is the fact that they are negatives. And what's different is when the two signs are different, then is when we have a problem. And adding of two negatives works exactly like adding of two positives. And so if we wanted to summarize these with rules, and our book has these these general rules as basically rules or theorems that have been developed for integer arithmetic. But what it says is a plus -b is equal to a minus b. But, as we're looking at a couple of these examples, what we can see is that if we add a negative to a positive, it has a subtractive effect, because positives and negatives offset one another because they are opposites. So if we're trying to reason why this is true, again, we've seen this in this particular case, but I could kind of reference this using a conceptual word if I was trying to explain, like adding a negative is subtractive. And this is kind of why we reuse the same symbol at the end of the day, because adding a negative is the same as subtraction. Now, as I was saying, negatives and subtraction are not the same thing, but functionally speaking, adding a negative, adding debt to, to your bank account is the same as taking money away. You will have to pay it off eventually, and technically there may be ways around it, like dying, but that's not ideal. Now, similarly, let's say we have a negative plus a negative. What it says is that's equal to -a plus b. Or as I was saying, if we were to add the raw values, the absolute values of those numbers together, we would get a larger negative. But essentially, adding two negatives makes a larger negative, is another way I could say that. That's just kind of how I would describe this idea as a conceptual sentence. But it's like if I have a debt and I add more debt, I'm going to be in deeper cumulative debt, and the sum of two negatives is the ultimate sum of their absolute values. Now, so shifting into subtraction, so I kind of maybe should have paused the video here, but the other video is just getting long, is subtraction means take away. So all of the same ideas we were saying about addition, we could just change to subtraction instead. And let's say we were going to use the chip model. Well, it's a little bit trickier with subtraction, so let me show you how I would think about it. So say I had 4 and I wanted to take away -3. The issue with 4 is that I can't take away -3 because there are no -3s in 4. So what I could start by doing is I could add in 3 positives and 3 negatives to begin with, because this is equivalent to the number 4, right? If I was thinking about 4, the original description of it, that's the same as 7 minus 3. And of course, or 7 plus -3, whatever you want to say. Now, this is a weird way to look at 4, but notice that in this case, in order to take away a negative, I need to have negatives to begin with. And originally speaking, I don't actually have negatives, so I will get completely stuck. But if I wanted to do 4 minus a -3, I could do that now that I've rewritten 4, and I could actually take those away. And so notice I'm not canceling because it's not adding. I'm not canceling out negatives with positives. I'm adding 3 negatives to my thing so that I can have enough positives. But anyways, the answer that I'm left with here is 7. Because in order to take away debt from a positive, it's going to need to become larger. And this is another thing. If I'm taking away debt, that's actually a positive action. Kind of as we said previously, if I have a double negative, that actually makes addition. And the same thing is true if we go back and look at rule number 1, or I forget how these theorems are numbered in our textbook, but it says a minus a negative b is actually addition, because the opposite of subtraction is addition. Again, it makes a lot of sense when you think about opposites. And if we think about the chip model, well, 4 to begin with has no negatives. How do I take away a negative if I don't have it to begin with? But I can think about 4 as the difference between 7 and 3. And if I think about it as 7 plus a negative 3, I have enough negatives to take away. And what I would be left with after I take away 3 negatives from 4 is 7. Again, it's kind of weird. I think kids will not be super happy about this, but they can still try to learn the rules of the chip model in order to do it. Of course, you can see the preferable nature of using the algebraic side of things, where we can, as I remember my teacher doing it, kind of changing these both into pluses like that and being cool. But again, we don't want to lose the meaning of why that happens. And again, the whole opposite thing just makes it so much easier. The opposite of subtraction is addition. And similarly, again, this should be 10. We all know that right away based on the rule. But if we were trying to think about it in the same light, again, if I start with 3, the problem is I cannot take away negative 7 from this. So I want to add 7 positives and 7 negatives, because I'm allowed to do this with the chip model, right? As long as I balance it out, the balance of all the chips in this will be 7. Sorry, will be 3, because I just added in 7 negatives, 7 positives, and I had 3 to begin with. So the total value of chips here is 3. And in the rule, if you're trying to say, how do I explain this to a kid using rules, you're always allowed to add 1 positive and 1 negative if you want to, because ultimately that's a net 0 in the chip universe, or the set of all the chips that we're working with. And again, if I now I can take away, right? Because what this says is if I have 3 positives, how do I take away 7 negatives? I was not able to, but now I am able to, right? Now I'm able to take away 7 negatives. I just subtract the 7 negatives. And what that would leave me with is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I end up with 10 positive chips. And again, as we know, taking away a negative ends up being additive. And this helps us to understand why does that work like that. Because in order to take away debt from something, taking away debt is positive, and we needed more positives to begin with in order to do that. Now, let's say we were just let's look at a couple of these other examples, because these are all a little bit different. But say we wanted to have negative 5 and take away 5. Let's say we put the negative first in the minuend versus the subtrahend, because these are examples where we're the minuend is positive and the subtrahend is negative, and those all work one way. It can be very different if you swap those. And again, you want to mix up your examples as you're working with kids and showing them these different techniques, because again, there's different rules you can establish in each case. But here, again, if we focus on the concept, I'm starting with negative 5. So that's my original number. And I'm trying to take away 5 from negative 5. But notice that this is a positive. It's the same exact situation as I was describing, because I can't take away 5. I don't have 5, right? These are negatives. These are not positives. This one's taking away a positive from here. So in order to get more, well, I need to add 5 of each in order to actually have enough to subtract, right? So I'm going to add 5 reds and 5 blacks, because now we have, again, this equates to negative 5, the original minuend. And now I actually have, the goal was to take away 5 positives. Now I have 5 positives to take away 1, 2, 3, 4, 5. And what I'm left with is negative 10 negatives. And as we know, if you here we have a negative minus a positive. Again, this is a completely different situation. I've seen people build these rules like negative minus negative, do this. Negative minus positive, positive minus negative, and have all sorts of rules to do. I don't really suggest teaching kids those rules, at least not first, because most likely they're going to misremember them or use them and get the wrong answer. And they're just going to be confused. They're going to be frustrated because they're not going to really get it. Now, the chip model is still pretty annoying, but it gives us more sensibility behind why does this end up becoming a larger negative. And this, if we kind of put the first 2 rules up here together, you could actually change subtraction to addition of a negative. So this is another way of thinking about it if we're thinking about it more algebraically. But by rule 1 above, I could rewrite this as -5 plus -5, right? Because what this rule states is that adding a negative is the same as subtraction. But I could think about that backwards, right? Subtraction is the same as adding a negative. So here, subtraction is the same as adding two negatives. And what I end up having is, well, those are both negatives. When I add two negatives, that makes a larger negative. So this answer of -10 makes a lot more sense. This might make more sense to you than how I was explaining it before. But again, they're all just, ultimately, we want lots of different ways to try to understand something. Different conceptual methods will give us a better, greater understanding of these properties. Again, math is not something that's learned overnight. It takes lots of practice, lots of different techniques. But ultimately, we can learn a lot of these rules for positive and negatives without needing to memorize anything. The next one, actually, this one is way, way easier with the chip model when they're both negatives. And again, when we're taking them away. So again, we're developing more elaborate examples where, again, we could use the double negative makes a positive rule to do this, but let's not. Because again, let's try to focus on subtraction. Because what this is saying is we're going to start with -4. And we want to take away -3. So actually notice this one, we don't need to do this whole weird thing first because we actually have negatives to take away. If I take away 3 negatives from 4 negatives, what I have is a single -1 left over. So this is actually really, really easy if we think about it conceptually, because if I have 4 negatives, if I take away 3, I'm going to be left with 1. But, again, how most students would do this is, well, if I have -4 plus 3, again, lots and lots of different ways to conceptualize that. There's not one unique way of figuring out the answer, but this way, very, very easy to see why we get -1. Now, if we're using a number line model, this can also be helpful, but, say we're starting at 0 and, I'm going to go to -4 because that's where I'm going to begin this problem. If I want to take away a -3, the other thing to, if you're trying to use the number line model, it's all about, am I going to the right or to the left? And 2 negatives make a positive. So the action here is going to the right. So if I want to take away a negative, I actually want to move to the right. I'm going to end up at -1 because, again, another way of thinking about double negative is +3. So if I want a +3, I'm just going to move to the right from my minuend 3. And that would, of course, leave me at -1. And again, having different ways of figuring out the answer will give your kids ways of checking themselves, thinking about it. Of course, calculators can also do integer arithmetic just fine. Now, another situation is, say we just have a straight up subtraction problem that involves only positive numbers. So if we were working with just whole numbers, this demonstrates the fact that the whole numbers are not closed and we can't solve this. So when your kids are first learning subtraction, might be a stumbling block. This might be a position where they get stuck. But once we introduce the negatives in the chip models, they can now figure it out. Because if I want to do 4 take away 6, well, if I have 4, I don't have enough to take away 6. But what I could do is I could add in 2 reds and add in 2 blacks. I'm always allowed to add in the same number of both to my chip bin, because ultimately that is still equal to 4. And now I can actually take away 6, right? So now that I have 6 blacks and 2 reds, which is 4, I can take away 6 from 4. And what that leaves me with is 2 reds, or -2. Or a rule you can establish that if you're trying to take away more than you have, you are allowed to do that. You just get negative answers. And if we're thinking about the number line method, again, very, very helpful for these examples, 1, 2, 3, 4 over here, I can take away 6. I'm allowed to go beyond 0. I can take away more than I have. That just sends me into the negative side of things. Much, much easier way of thinking about that example. Or, say we had another case where we wanted to take away more than we had in the case of a positive. If I was using this one on the number line method, again, I'm going to start on the left. So I'm going to start down here on -5. And I want to take away 9. So that's going left even further. And at the end of the day, I can just focus on the numbers themselves. This is going to be an additive effect because I have a negative plus a negative, essentially, or subtraction is the same as adding a negative, and I'm going to end up with 14. And of course, it will be on the negative side of things because it is negative. And again, if we're trying to explain these rules, you can do so in the fact that, well, the opposite of subtraction is addition. Similarly, this other rule actually is, we could communicate in the form of this example right here. But what this rule is saying is, if I have a negative minus a negative, it's just equal to b minus a. But so if I was thinking about this rule algebraically, let's write this one over here just as in if you're trying to take notes. If I have negative a minus negative b, I could use rule from right here to say, well, two negatives. I could use rule number 1 to say, well, if I'm subtracting a negative, that's the same as addition, a negative a plus b. But since addition is commutative, I could rearrange this as b plus negative a. Again, you don't need to write parentheses around negatives, but normally, notice I have been writing the parentheses, but don't have to write those parentheses. It's good practice to do so. And I don't know if you were wondering why I have parentheses around everything. They're not mandatory. But now notice that I have, since addition is commutative, I have b plus negative a. Well, of course, as we know, adding a negative is the same as subtracting. That's this rule right here. So what I've just shown is that negative a minus negative b is equal to b minus a. And if we try to apply those rules, let's say we could do that here. If we have a negative subtracting another negative, you could just subtract the two numbers. 3 minus 4 is negative 1. Notice that trick works. If you reverse it and subtract, we're going to get the right answer. Kind of cool. You may have not known that trick works. But again, certain tactics and tricks that we try to teach our kids, they're going to have trouble with if they don't really get why. And, building these rules, it's kind of like a bunch of building blocks, right? If we want to understand the rules, we have to get why they're true. And we can use simpler rules to build up to more complicated rules. That's the essence of theoretical math and how it works. And if you use that logic with your kids too, they'll begin to understand, okay, this means this and this means this. So if I use more of these elaborate theorems, I can build more complicated rules to simplify tactics. And these are all the fundamental ideas of algebra, which eventually they will need to learn, and they'll have a better understanding of why math needs theorems and so forth in algebra. But one last rule says if I have a negative a minus b, it's equal to negative a plus b. Basically, it's just a combination of these two rules. Notice if we look at the right-hand side, we have negative a plus b in both cases. But here if we have a negative plus a negative, it's equal to a negative. But here we have a negative minus a positive. But remember, another idea that I was trying to establish is that if I subtract a positive, it's the same as adding a negative. And actually, that's really what this rule says here. Adding a negative is the same as subtracting a positive. And that's kind of what we're doing here. I'm changing a negative b to adding a negative, and then I'm applying this rule as well. So let me try to sketch this out if you're having difficulty following what I'm trying to say. Let's start with negative a minus b. I could rewrite this as negative a plus negative b by this rule right here, because subtraction is the same as adding a negative. Now that I have adding of two negatives, I could use this prior rule. When they're both negatives and I'm adding them together, I get a larger positive. So what I get is negative a plus b, or you could think about that as the distributive property. The negative will factor out of the common numbers. But notice, my point was, if we look at this example, notice that same sign. So there's a saying that derives from all this, and that's kind of my point in that. Same signs add, opposite signs subtract. So notice when I have the same sign, negative, negative, subtract, negative, negative. Sorry, same signs add, negative, negative, add, negative, negative, add. But the signs stick to them. So when you're adding two negative things together, I get a larger negative. Opposite signs subtract. So notice that these are really the same sign because it's positive, positive. Same signs add. Opposite signs subtract. So positive, negative, subtract. Positive, negative, positive, subtract. Same sign add. It's kind of a tricky rule, but that's very, very helpful for students once they get the idea of, is the number I'm trying to get, do I need, the question is, am I adding the two numbers or subtracting? And that is ultimately a difficult question to answer. And with the final bullet point, it says, can you explain why integer addition is commutative but subtraction is not? Well, again, if we're going back to our conception of subtraction as a additive comparison, again, I like the example 7 minus 5 and 5 minus 7. Subtraction is never commutative, and this includes positives and negative numbers. And if we throw in other numbers, like say we wanted to do 7 minus -5, and I was to do -5 minus 7. I was imagining switching the order. Well, here I'm taking away negative, which is positive. This is additive 12. This is still additive because same signs add. But notice that this, if I start with a negative and take away more, what's different is the sign of the answer. This one is positive 12, whereas this one is negative 12. And another thing that is important to remember with subtraction is while it is not commutative, when you reverse the order of subtraction, you get the same sign regardless. Sorry, you get the same answer regardless, you just get a different sign. And if we go back to our rule for subtraction, if you remember I said this a couple classes ago, but say we're trying to subtract 42 minus 19. However we do that, we're going to get 23 as our answer. Oops, you can't see what I'm writing. There we go. But let's say our students are facing a backwards problem, 19 minus 42. The way we teach them to do, if you can't subtract, if you're taking away more than you have, what you do is you reverse the operation. So we'd solve this the same way as we solve a positive problem. The reason is the answer is negative. A lot of students forget that we have to change the sign to this answer to a negative after all is said and done. Again, because of this exact reason. If we're taking away more than we have, we're going to end up with a negative number. But the answer will be the same. So it's sort of like examining commutativity. Subtraction is not commutative, but we can switch the operation if we switch the sign of our answer. Just like in this example, right? This is 2, this is -2. We can get the answer, the absolute value of the answer, using a typical algorithm. But my point is, the standard algorithm is not built to solve this problem. However, if we use the negatives algorithm, which I've showed you guys in class, we don't need to worry about those little rules, right? Because if I just use the negatives algorithm, well, 2 minus 9 is -7, and 40 minus 10 is 30. If I do 30 take away 7, I get 23. And so I don't have to remember those little rules that we may have to with the standard algorithm. And there's advantages to some algorithms over others, as we've discussed. So in the next video, let's get into multiplication and so on. And we can pick up some of this after break if we need to.